Alright, so I've split this video up into two parts, so this is going to be the second part. In this one I'm going to talk a bit more about R. I'm going to elaborate a little bit on one of the examples that I gave in the first part of this video, and then walk through a second example. Okay, so the first thing that I've done is I have two windows here, so I have the R command line here on the right, and I also have an R script, an R file here on the left. The reason is because I don't want to try and remember all the things that I need to do. But I'm going to walk through this file here line by line. Okay, so the first thing that I've got here is I have this vector of values. So you might remember that from the first video we said that we can define a variable, so in this case shots, and I can assign to it this vector, which we start by saying C, open parentheses, insert all of our values and close parentheses, and we do that assignment with the less than arrow and a dash. And this is the game-by-game list of shots for Alexander Ovechkin from the 2018-2019 season. So we brought that into memory. Okay, so now the next thing that we can do is we can take a sample. So this has given me a sample of 10 games from all of these shots. Right, so the shot results that we get for this are 8, 3, 5, 6, 0, 2, 4, 6, 8, and 2. I didn't pick the way the last ones would come out, but it's kind of interesting that it worked that way. Okay, so then we might be interested in, well, what is the average number of shots that we get from this sample? From the sample, we get 4.4 shots over this 10-game sample. As you might remember, I said that the correct average for the shots is about 4.17. We could see that from here, a bit over 4.17. So a sample of 4.4 is actually pretty close to the exact value. Okay, so one thing that we could do is we could look at what's called the frequency. So we could take the table of our games. Right, so remember that we said last time this is just going to count how often each number shows up. So we have a pair of 2s, so we get 2 there. We have a pair of 8s, and we have a pair of 6s. So we get 2 for those entries, and then we have one game with 0 shots, one with 3, one with 4, one with 5. Okay, so from our sample we could ask how often does each of these values appear? So we could take frequency and divide by the sum of frequency. So from our sample, 10% of the games sampled, so 1 out of 10, results in 0 shots. 20%, 2 out of 10, give us 2 shots, and so on and so forth. We can also use a function for cumulative sum. And what this one is doing is it is taking the line here and it is summing up every entry to the left. So for example, there are 10% of the games have 0 shots. 30% of the games have at most 2 shots. So we take the 10% that were 0 shots, the 20% that were 2 shots. 40% of the games have at most 3 shots, so the 10% from 0, the 20% from 2, and the 10% from 3, and so on. And one thing that we can clearly see is that for our sample, 100% have at most 8 shots. The only values that showed up were 0, 2, 3, 4, 5, 6, and 8. So obviously the biggest value that we have showing up is 8, and 100% will have at most 8 shots. Okay, then we can also call a function called summary, and that gives us a couple of values. So if we call summary on the entire shots vector, we get the minimum value, which is 0, so 0 shots per game. The maximum value, we can see here, is 11 shots per game. And then we get these 4 values in the middle. So we have the mean, the average, which we'd already said was about 4.17. And then we have these other 3. So we have the median, the first quartile, and the third quartile. So the median for any data set is the middle value. In this case, there are 81 values in that shots vector, so we pick the middle value, which in this case is, if we were to order all of the shots, the 41st value. Right, so if I were to call, so if I were to sort shots and take the 41st entry, one thing to keep in mind is that R starts counting vectors from, in this case, 1 up to 81. If you did this in a different language, you would get the count going, you could get the count going from 0 up to 80. So it's worth keeping in mind how counting is done. If you've never done any computer programming at all, this is the most intuitive way that it would work, but if you've done some other languages, Python, Java, for example, the count starts at 0, so just be careful with that. So if I were to sort my shots vector and I take the 41st entry, I get 4, which is the median value here. If we had an even number of entries, so in this case Ovechkin missed one game if he had played in all 82 games, to get the median we would take the average of the 41st and 42nd games, so the average of the two around the middle. Okay, and then there's this first quartile and third quartile. So what those are representing is effectively the median of the bottom half of values for the first quartile and the median of the upper half of values, which is our third quartile. Or in other words, kind of the value, the 25th percent value and the 75th percent value. So in this case, what we can do is we can call the median of sorting all of our shots and then looking at the bottom half. So in this case, I'm going to take values 1 through 41. And for the top half, I'm going to take values 41 through 81. So I'm using that 41st value twice. And if we do that, we get 3. And if we take the median for our top half, we get 5, which is exactly what's coming here from the summary. Okay, so we could also go and look at what's called the variance. So we know from this that Ovechkin was getting just about 4.17 shots per game. But we see that there's a sizable bit of variation here. There's one game where he had 0 shots. There's another one where he had 11. So what we might also want to see is we know his average number of shots, but how much unpredictability, maybe how much well, the formal term is variance. So how much does his shot how much do his shots vary from that average for a given game? And the way you calculate that is with what I've said is called the variance. Okay, so the variance is to measure how far away you are from the average. So the first way you might think to do that is to go and start using absolute values. And that is a perfectly reasonable approach. The reason why we don't use absolute values has reasons to do with calculus, with derivatives and such that we're not going to really get into. So what we will do instead of using absolute values is we will square the difference in values. And the reason for that is it has the same kind of effect as taking absolute values, but it makes any derivatives that you would want to do if you were looking at the calculus kind of aspect, it'd be much easier. Okay, so what we do is we sum up for each shot. We take the difference between that shot value and the average, which is what we're taking here. We then square that value, and then we divide the entire thing by the number of shots minus 1. So in this case, we're going to divide by 80. Okay, and when we do that, we get that our variance for our shots is about 4.5. So what that would say is that for a typical game, you would expect the bulk of the shots that the bulk of the games, the number of shots for Ovechkin is going to be within 4.17 plus or minus the square root of the variance. And the square root of the variance is referred to as the standard deviation. Okay, so to just maybe make it a little bit more clear what we're doing is we're taking, I'll just pull up the vector so I've got it here. So what we would be doing is we would be saying we are going to take 5 minus our average number of shots, and then we're going to square that. So we would have 5 minus the 4.17, so about 6 or 0.68. So I would have 5 minus my average shots squared. And then I would add to that 3 minus my average shots squared. So notice that, well, 5, the first game is above average, the second game is below average, but we're only looking at how far away each entry is from the average. So we're looking at positive values, right? So we'll get our 3 minus average shots, that'll give us something positive. Right, and then we would keep on adding all of these up. So then the next one we'd have would be 7 minus the average shots squared, and so on and so forth. And then we would divide the entire thing by 80. And when we do that, we get this value of about 4.5. And if we wanted, we could instead of calculating it on our own, we could just call var shots. So that will give us the variance of our shots, which we see is this value of about 4.5 that we just calculated. If instead we wanted to calculate the standard deviation of the shots, so that'll give us the square root of this variance, we get about 2.13. And if we call the standard deviation of the shots and square it, that gives us the variance. Okay, so that's one thing that we could do. So then the next thing that I've done, sticking with this hockey theme, is I've taken all of the players that played in the NHL in the 2018-2019 season. The reason I'm going back there is because last year the entire season got interrupted, so I'll just take the last full season that we have. And what I've done here is I have put all of the player data into a comma separated values file, so a .csv, and I've got it saved at an address on my hard drive, and I'll put this file, I'll put this R file, and I'll put the CSV file up into Discovery so you can play around with them if you would like. Okay, so those are all of my players. We can get a preview of the file by calling head players, so that will give us the first, in this case, 6 entries for our file. I've sorted everything alphabetically by player ID, so the first player that we have alphabetically is Justin Abdelkader. I think he was playing for Detroit. I forget offhand where the rest of these players were playing from, so the variables that I've kept for each player are the ID, the name, the country of birth, the position where I've put it as forward, defense, or goalie, the height and weight of each player. The other thing you could do is you could look at the final entries in the file, so that you would call by calling tail of players. And in this case, we get the final 6 entries. Okay, so let's see. So we want to talk about how we could display data. So one way that we can display data is with a histogram. So what I'm going to call is I'm going to call a histogram of the player's data using only the height variable. So I'm only going to concern myself with this column, and I'm going to call a histogram for all of that. So what's going to happen is, for completeness, my height is in inches here. So we're going to take all of the players by height, put them all into little categories based on how many players there are of that height. So for example, I'll get the total number of players that are 74 inches, so 6'2", all of the players that are 71 inches, 5'11", all of the ones that are 69 inches, which is 5'9", and so on, and make a plot of that. And what we're doing here is we take the data file, so players, use the $sign to get a particular column. So if I wanted to get position, I would do $sign position. If I wanted to do weight, I would call $sign weight, and so on. Okay, and when we do that, we get this kind of plot. What this says is that the most players are 72 inches, which is exactly 6 feet tall. The next most common height that we see is 6'1", so 73 inches, and so on. There are a couple of players that are down here at 69, 68, 67, 66, so 5'6", and there's one player over here at 79 inches, so 6'9". That one you might guess correctly is Zdeno Chara of Boston. So if we wanted, we could also call that summary for height. And what we see is that the minimum value is 66 inches. The 25th percentile value is 72 inches, so 6 feet tall. The median, so if we were to sort, if we were to put all of the players in a line going from shortest to tallest, and we were to pick the middle player, that player would be 6'1". The average value for all of the players is a little bit over 6'1". Our 75th value is, I guess, somewhat conveniently 75 inches tall, and the tallest player is 81 inches. That's 6'9", and that's still Chara. One thing that we can observe from this is that the mean is ever so slightly greater than the median, and the textbook notes that whenever the mean is greater than the median, in this case it's only very slight, but different data sets it could be substantially. Your data is what we would refer to as skewed to the right. And if the mean is less than the median, we would say that the data is skewed to the left. Okay. The other thing that we see here on the y-axis is just the total number of players that fall into each category. So from this one, we see that the total number of players who are, in this case, 5'11", is just a little bit over 150. There are a little bit over 100 players who are 5'10". I don't know, I'd say there are about 60 players or so that are 5'9", thereabouts. And then outside of, well, I guess below 5'9" and above 6'3", comparatively very few players. And that kind of makes sense. There aren't going to be that many hockey players that are very tall, and there aren't going to be very many that are very short. Okay, so one other thing that might be of interest is what happens when we look at a subset of our data. So the players object has all of the data for all of the players. But what I'm going to do now is just take another histogram of heights, but I'm only going to look at the goalies. So when we go and open up these square parentheses, it will go and look at just a subset of the data that meets a certain condition. So what I'm doing here is I'm saying, give me all of the rows so that the position value is a G, or in this case is a goalie. So the separation here by putting this information to the left of this comma is saying look at only the rows. If you did something over here, as I managed to do up above here, it does some, when you go and you put something to the right, it goes and starts picking stuff off by commas, by columns. That's not what you want to do. So what this is doing is saying, give me the subset of the player's data frame that only looks at the players who have a G for their position. So look at all of the goalies and then call a histogram on the height for those goalies. There. Okay. So what do we see here? Well, when we just had the histogram for all of the players, what we saw is that the biggest heights, kind of the center of that data, was around 6 feet and 6'1". So it was these two columns. But now for goalies, what we see is that the most goalies, so about I think 25 goalies, are at about 73 inches, which would be 6'1". So that's where we see the most. What we also see is a lot of goalies that are bigger than that, and not too many that are shorter by comparison. So there are about as many here that would be 6 feet tall here that are 6'2", but then we see other ones 6'3", 6'4", 6'5", 6'6", and so on, and not too many short ones. And this kind of makes sense if you think about goalies, because you want someone who's going to take up a lot of space, and you get a lot of these taller players. So I think Ben Bishop with Dallas is about 6'7", and you see a lot of these very, very tall players showing up at goalie. But then if we go and instead look at a histogram of forwards, what we see is that they're going to be maybe, you get more of the small players are going to be forwards, effectively. So what we see is with forwards, the most common height here is 5'11", whereas the most common height over all players was 6 feet. And then we see there fair number of smaller forwards. So you get players like Johnny Gaudreau of Calgary, who's about 5'9". You'll get those. You won't get that many small defensemen. So again, same kind of thing. The defenseman histogram kind of looks like the goalie one. Defensemen are naturally going to be taller. So a lot of this kind of nicely conforms to what we might expect for hockey players. Okay, so another way that we could display data is with what's called a box plot. So the same data, I've taken the box plot and I've gone and plotted all of the heights for the players. So there are a few pieces of information that a box plot gives you. So one that a box plot gives you is this box in the middle. So it gives you the median, which in this case is this solid black line, which is 73. The 75th percentile, so that third quartile value here is going to be 75. The 25th percentile value, so that that first quartile, is 72. And then we get these two lines here which give us the biggest value that is not an outlier. The definition of an outlier is something that we can come back to later, but for the moment we can just take it as an unexpected value, we'll say. And then the smallest value that's also not an outlier. And then these two circles give outlier values. So what we see is the biggest value here is at 81, so that one's Zdeno Chara. This one is at 80. I'm not sure offhand who that would be, but let's find out. So I'm going to take a subset of my players so that my height is at least 80. And I forgot that comma there. Okay, so yeah, so Tyler Myers, I don't know, I guess he would be with either Winnipeg or Vancouver in that year. So Tyler Myers is 6'8". Zdeno Chara is 6'9". Those are these two outlier values here because they're kind of both freakishly tall. And then we could look at these two small values here. So these two small values would be, I think, let's see, less than or equal to 67. So that would be 5'7" and below. One thing that we can see is that this dot here is kind of thicker than this one, and that's saying that there are more of these values. And that kind of makes sense here because there are 3 players that are 5'7". There's one that's 5'6". So Alex DeBrincat, I think, with Chicago is 5'7". And then offhand, I don't know what teams the other 3 players are on. But these are all outlier values. And then this solid line here is the smallest value that's not an outlier. Okay. And then the last thing I want to do is just give an example of another kind of histogram plot. The reason why I need to do something slightly different is that I'm going to just do a histogram for all of the countries. So height is a numeric value, it's a number in inches, but country is something that we would call categorical. So you have the country, you have Canada, America, Sweden, and so on. And these are just done by categories. You can't do a histogram plot with categories. If I try to do a histogram plot with just categories, I call players and I call country. It doesn't work, so it tells us So what this is saying is that the values you give have to be numeric. What I'm trying to do here is feed to the histogram a bunch of countries. So I'm trying to feed it strings like Canada, United States, Sweden, and so on. It doesn't work. But there is a way of plotting a histogram for categorical values. So we can do it with this command that I have nicely written here. So we see from this histogram for all the categorical values is maybe a very unsurprising result is that most of the players in the NHL are from Canada. The next most common country that they come from is the United States. Following that, Sweden. For some of these, yeah, okay, so after Sweden is Finland. And then after that, we have these four here. The country abbreviations are maybe sort of obvious, but maybe not. So RU, as you might guess, is Russia, but SU is the Soviet Union. So for players who were born, I don't know, before the late 80s, 1990, something like that, they would be born in formerly the Soviet Union. So Alexander Ovechkin would qualify in this category because he was born in the Soviet Union, not Russia. This category is also similar. So CZ is the Czech Republic, but CS is Czechoslovakia. So someone who was born before the Czech Republic and Slovakia split, I think that was in 1991, would be in the CS category. So I think, so Zdeno Chara, for example, he's born into what is now Slovakia, but when he was born it was Czechoslovakia, so he would be CS as opposed to CZ. So some minor interesting bits, but this also tells us a way that we can go and plot histograms for different kinds of values. So this is maybe something to keep in mind depending on what you would plan on doing maybe with a project going forward. Okay, so I think that about wraps up everything I wanted to say with R in this video, and I will see you next time.